All right. Hi there to everyone watching the recording. I did want to start off with a couple of notes about your proofs and your web work assignments. There are a couple of broken web work questions that have to do with sets. So if the web work question says that there's an error on it, just skip it and I won't count that toward your grade. Another note on the web work is there's a slight difference between the web work definitions and your book's definitions, similar to the difference last week. Your book says that a forest can't be a single tree, but the web work says that it is, right? So there's a question on web work where it's like shows you 4 graphs and it says, oh, which one of these is a tree and which one is a forest? For that one, if it's a tree, then it's also a forest. It's just a one tree forest, which is slightly different than your book's interpretation of those words. The reason why WebWork does that is because that's how everyone else does it. And your book is just being weird. And there's a couple of questions in the WebWork that have that issue. So do bear in mind that a single tree does count as a forest in terms of WebWork. Another issue was your right? So another issue was on your proofs. I asked you to find an expected value of the distance of a randomly chosen vertex from the nearest leaf in a full tree, in a full binary tree. What I meant by that was a complete binary tree, which makes the problem quite a bit easier. Otherwise, you can't really answer the question if the tree is full because you don't know which of the, you don't know what the distances are. So this tree is full. And for this one, you don't know if it's full, whether, these guys actually exist on there or not, right? So if you would please reinterpret that question. And in fact, maybe I should change it right now. If you would reinterpret that question to say a complete binary tree, instead of a full binary tree, so that you do have all the possible children at every level. And I believe that's your graded proof this week. Is that right? Or is that one of the collaborative ones? But it doesn't matter either way. You should interpret that as the tree being totally filled and therefore complete. That's the graded one. Yeah, for sure. Otherwise, you can't really answer the question. It is one of the collabs. Okay. Yeah. So interpret that to be complete, and that'd be great. Oh yeah, the graded one is the spanning tree question, right? Okay, so that's all my notes for you. And now that I have quite a few more people in here, does anyone have any other questions for me before we jump in? For Dijkstra's algorithm, is it intentionally complicated to encourage you to automate it? I'm sorry, which question is that, Lucas? Is that one of the web work questions? 10.7.5. Let's take a look. I don't know off the top of my head. All right, so we want 10.7.5. Let me do that. Oh, yeah. Let's just do this. 10.7.10. Okay. Great. Okay, cool. 10.7.10. I don't know. I think you could do this by hand if you did a couple first, and you got sort of the spirit of the algorithm. I think you could do this. I think this is kind of on the edge between between it being shorter to automate it versus shorter to do it by hand. I think this might be right about on the boundary, where either it's kind of it's going to take a while either way, right? What I can suggest, if you don't want to code it up by hand yourself, you don't have to. There are plenty of websites that you can find where you can input a graph and it'll just show you Dijkstra's algorithm, which kind of defeats the purpose a little bit. But you certainly could do that if you wanted to, if you're trying to save time. But if you're not trying to save time and you want to actually go through a decent example and see how it works, then I think either way of automating or doing it by hand would be appropriate in this case. Yeah, it's kind of right on that level of difficulty where it could go either way, in my opinion. What do the rest of you guys think? Do the rest of you guys, have you done it by hand? Has anyone done it by hand? Has anyone automated it? What are your thoughts on that? Oh, this is one of the broken questions. Oh, really? Well, then that would solve that, wouldn't it? So A is broken, but B is not. Okay. Well, if they're listed in order, it shouldn't be a set, but it is giving you an error here. Let me try. Okay. NQTSB. I'm just putting in random stuff. That's not the answer. I'm just making it up. Let's put 5.7. Okay, let's see if it gives me an error here. Yeah, it is broken. Okay, well, in that case, that makes the question a bit easier. Just do part B, and that'll be a little bit easier at least. And for that, at least you don't have to make the big chart for Dijkstra that we're going to talk about later on today. So I'll just leave that as a practice question. So don't worry about part A, just fill in part B. And if you want to do part A, then that'll be just a little bit of additional practice for you. Does that sound good? Great. Sounds good. Okay, cool. Okay, other questions for me. What else can I help with? Alrighty. Well, in that case, I did want to start off with a really nice proof that demonstrates a new kind of proof technique, and it's similar to one of your proofs, one of your collaborative proofs for this week, which is listing out all of the non-isomorphic trees with 6 vertices, right? That's one of your proofs this week. And so for example, here's a tree with 6 vertices, right? And here's another tree with 6 vertices. Right? And obviously these are non-isomorphic, right? And one of your proofs is to list out all of them, right? But the thing is, there's not a nice formula. There's not like a closed form where you can put in how many vertices there are and the formula gives out how many non-isomorphic trees there are for that amount of vertices. There's not a nice formula for that, it turns out, right? What there is a nice formula for is how many directed trees there are for a given number of vertices, which is a little bit different, right? So here's one example of a directed tree, right? There's one of them, right? And then here's, sorry, my computer's being weird. There we go. And here's another example of that same tree, right? But since the directions on this one are different, right? These two guys are pointing inward instead of outward. These two trees now are non-isomorphic for a directed tree, right? And it turns out that there is a nice formula to count how many directed trees there are, even though there's not a nice formula to count out how many non-directed trees there are. So let me ask you this. Let me see if you can sort of get a handle on what's going on here. Are there going to be more distinct, and by distinct I mean non-isomorphic, are there going to be more distinct undirected trees or more distinct directed trees? What do you think? More directed. Yeah, exactly. Right. And that's because you can change which direction all the arrows are going on the same shape of the graph. Right. So, on this one, you have two choices for this arrow, two for this one, two for all of these. So this graph itself, since you can change the direction of all the arrows, right, is going to have a lot more. But let me ask you this. Is this directed tree isomorphic to this directed tree or not? Do you think these two directed trees are isomorphic or non-isomorphic? Sean, which one, Sean? I'm not sure what you mean. They are isomorphic. Good. Because even though the order of who's going in and out changes, it's not about the order because you can just scooch around which arrows are where, right? It's not about shape, it's about number. And Sean, that's exactly right. 3 out, 2 in means these two guys are isomorphic. People happy with that? Does that make sense? Got it. Cool. Okay. So what we're going to do is we're going to prove, quick question. What if we had distinct vertices? Not sure what you mean by that, David. Distinct vertices? So that's another way to think about trees or graphs in general, is labeled trees versus unlabeled trees, right? The point of isomorphism is that the vertices could be named differently, but the shape of the graph is still the same. That's right. The idea is that you can switch labels on the vertices and the graphs still have the same shape, right? So even though they're labeled, isomorphic means that you can switch where the labels are in such a way that the same exact shape pops out. So maybe I should do an example of that, right? So if I have, this guy, right, A, B, C, D, E, where now I've labeled the vertices, then I have this star, right? Then if I start with A up here and I go down, let's go down this way, right? So A has to connect to B on one side, right? And then E on the other side, right? So then E would have to come down here, right? And B connects to A and C, so C comes over here. E connects to A and D, so D is over there, right? And so these are still labeled, and the labels are the same, but they are still isomorphic, right? Now, using a directed graph is a similar sort of way to get at the idea of labels, right? So let's jump in, right? So the idea is I want to, the idea of the proof is called a proof by double counting, okay? So what I'm gonna do is I'm gonna use our strategies from chapter 9 where we counted up how many different kinds of a thing there are, how many combinations we can do. I'm gonna use that idea to count up how many different combinations of these different edges we can have for these graphs, but I'm going to count them in 2 different ways. I'm going to count the same thing, which is the number of non-isomorphic directed trees, but I'm going to count it in 2 different ways, set those 2 different formulas equal to each other, which is going to, at the end of the day, give me a formula. Because since I count in two different ways that are equal, I'll get an equation that I can then reduce and is going to give me my answer. So it's called a proof by double counting, which is a kind of a nice, elegant way of finding a formula there. And David, you have a question. In the case of the directed graph, if A goes to B, C goes to B, is that different than B goes to A and B goes to C? Well, that's if you put on labels and directions, right? So that's a good question, actually. Let's think about that, right? So if I have A goes to B and C goes to B, so A goes to B and C goes to B, right? Is that the same thing as B goes to A and B goes to C? Well, that one wouldn't be, right? Because this one versus this one, here they're going outward and here they're going inward. So I would say these are non-isomorphic, right? But I would say that these ones, if I call this B, into A, into C like this, I would say these two here are isomorphic, even though the labels are different. Does that make sense? Yeah. Okay. So Cayley's formula, so let's do this. Let me, maybe I'll show you after break. Let's go through the proof and then I'll double check. I haven't looked at the wiki for this since last year. So over break, let me look at the wiki and then I'll see if there's a good example of the relationship between directionality and vertex labeling. To give you a nice clean example of the distinction there. But for now, let's just stick with the idea of directionality, and I think that's going to work for us, right? So what we're going to do is we're going to prove that the number of directed trees on n vertices is equal to n to the n minus 2 power, right? That's what we're shooting for. This is Cayley's formula. Right? Named after Arthur Cayley, British guy, 100 years ago, right? So here's what we're going to do. We're going to count the number of different directed trees in two different ways, okay? So here's method number one, okay? We're going to start with a tree. We're going to pick one of the n vertices to be the root. And then we're going to add the n minus 1 edges in any sequence. Okay, so let me give you an example, right? So I'm going to start with a tree. Okay, so here's a tree. Okay, there's a tree, right? Now what I'm going to do is I'm going to pick one of the vertices to be the root. Okay, so let's say I pick this one right here. This guy's going to be the root. Okay, so it has degree 3, so I'm going to start up here. It has degree 3, right? And now what I'm going to do is add the n minus 1 edges, right? So, so let's see. So how am I going to do that? Okay, so I want to add the edges in a sequence, and that's going to give me a directed tree. So I think what I'm going to want to do is each time I add an edge, okay, sorry. My brain is not totally on today. Let's try the other way real quick. I'm going to let my subconscious think about that for a second. Okay, here's way number 2. All right. We're going to add edges one by one to an empty graph. Okay. So step 1, assume n minus k edges have been added. So that there are k trees in a rooted forest. Okay, so let's think about that for a minute. So we've got some vertices here. Okay, how many vertices is that? 5, 6, 7, 8, 9. Okay, n equals 9. Let's say that k equals 3. So in that case, we're going to assume 6 edges have been added. So there should be 3 trees here, right? So we say, okay, so I'm going to add 1, 2, 3, 4, 5, 6. Right? Okay. Then to add the next edge, pick any vertex and any root except the chosen vertex root. Okay, so step 2, we're going to add a new edge. Okay, pick a vertex and any root except the chosen vertices root. To add an edge, I'm going to say pick any vertex and any root except that vertices root. So for example, on this guy here, let's say I pick this vertex, okay? I can pick any root to connect it to. So I could pick this one or this one. Those are the 2 roots, right? Except I can't go back to this root because that would make a cycle and that would ruin my tree, right? So for this one, for example, right? I could pick any other root, right? Except for this guy's root. So I could pick, again, this one or this one. Now this guy, I can't pick this one's root. I can only pick this one or this one, right? So for example, let's say that I pick this vertex. Oh, sorry. This vertex, and right. And I can't pick. I pick this vertex. I can't pick its root, but I can pick this one, for example, right? Okay. And how many choices do we get in that case? Okay, so that gives, we get n times k minus 1 choices, right? Because I have n vertices that I'm picking from, can pick any vertex. And which root can I connect it to? Well, any root except the one where in the tree that I'm at. And since there are k trees, right, there are k trees in my forest, right, I have k minus 1 choices because I can't connect back up to my same root because that would make a cycle, which is not allowed in my tree, right? Okay. So since we start with 2 trivial trees, the total number of choices that I can make in this case is going to be the product from n equals 2, k equals 2, pardon me, k equals 2 up to n of n times k minus 1. And how much is that going to be, do you think? Do we have to connect the vertices to a root or to any other vertices? We have to connect it to a root. Oh, did I do, sorry, I think I did this wrong. Boop, boop, boop. I have to connect this guy to a root. So this guy would have to go over to here, to a root. What is a root? Great question. So a root is a vertex that doesn't have anyone pointing at it. Does that make sense? Perfect. Okay, so what we're doing here, let me just back up for a second before I finish up. Let me back up. So what we're doing is we're trying to count all the different sequences in which we can build this directed tree. That's what we're actually counting, right? So we're not counting the number of trees, we're counting the number of ways you can build these trees. And that's what we're going to equate to each other, right? So here's one way of counting how to build the trees. You start out with the graph empty, say, okay, well, I'm going to, add in arrows until I have a tree, right? And to do that, you can pick any vertex you want and put an arrow to any root of any of the other trees in the forest except its own root, right? So for example, once I'm at this situation, I can pick any vertex in here, right? Here, that this one, any vertex you want, and I can point it at the root of the other tree. So for example, this vertex could point over here at this root. Yeah, it can't point at its own root, but it can point at the other one, right? Yes, the tree has to go in one direction. That's exactly right. Yeah, the tree, a directed tree here is going to go from sort of from top to bottom. So it's going to look kind of like this, where all the arrows point away from the root. Yeah, that's exactly right. Mm-hmm. Okay, so does this make more sense now? Is that better? Yeah, okay, cool. So we're going to start with 2 trivial trees. So we're going to start out with, just 2 arrows, right? And then what are we going to have here? Well, each time that we add a new arrow, we're going to multiply, because we're doing this arrow and this arrow and this arrow. So that's the multiplication rule we're going to be using. So we're going to multiply, and for each arrow that we put in, we pick any of the n vertices and then any of the k minus 1 roots at that time. So do you guys see where this formula comes from? Does that make sense? Yeah, definitely. So what we're going to do is each time that we add an arrow, this example's full. Let me do another example. Right? So I think that'll help. Okay, so we've got a bunch of vertices. Okay. Now what we're going to do is we're going to add in arrows, right? And the rule is you can add an arrow from any vertex you want, right? So the starting point, right, like this, the starting point of the arrow, you can pick any vertex, but the ending point of the arrow can only be the root of a different tree in the forest. Okay, so for example, if I put an arrow in here and I want to connect up this guy next, well, what I need to do is point it at any root of a tree in the remaining forest. And these seeds, these are all count as roots as well. So I could put in one just like this, and that's fine. Now let's say I want to do this one. Okay, now this one, I can connect to this guy, this guy, this guy, or this guy, any of the roots, right? These guys are not roots, these guys are leaves, so I can't connect to them, right? So here, let's say I connect to this one, okay? Now let's say I want to connect up this guy to another vertex. Well, I can't connect to the root of my own tree because that'll make a cycle, but I can connect to the root of a different tree like this one, right? Right, you see how that one was the root because it doesn't have anyone pointing at it, right? Now this one, I can connect, or here, let me do this one. This one I can connect to that one because this connects to a different root. And now if I want to connect up, let's say, I don't know, let's say this guy, I can't go back to my own tree. I can't go to any of the other vertices, these ones or this one, because those are not roots. So the only option I have left is connect this guy down to here. Does that example help? Does that seem a little better? Okay, so what I'm counting is the number of ways I can build a directed tree, a directed rooted tree, I guess I should say, right? And so the number of ways I can do that is going to be this formula. Why? Because at each step, I can pick any of the n vertices, connect it to the root of any of the k trees except the one I'm currently in. So that's k minus 1 different trees. Okay, so I can pick this one and I pick this one. So that's multiplying. And then I continue to do that and I pick the next arrow and I pick the next arrow and I pick the next arrow, which is why I'm multiplying here. This is a big product, right? So the number of sequences I can do to build this thing is going to be what? Well, now let me solve this this product here in a closed form. So why don't you guys start helping me out? So how can I simplify this product? Any ideas there? Okay, good. I can pull out n. So how many n's are there going to be in this product? Close. N to the n minus 2. Good. So I have n to the n minus 2. And then what am I going to have for my product from k equals 2 to n? How's that going to look? So that's going to be, this guy. Oh, and actually, I'm sorry, this won't be n minus 2. This will be n minus 1, right? Because if I went from 1 to n, that would be n n's, right? But if I go from 2 to n, that'll be n minus 1 n's, right? So this actually should be n minus 1 instead of n minus 2. Does that make sense? Cool. Okay. So we got an n minus 1 here. Great. And then this is going to be n minus 1 factorial, as you said, right? Because I'm going to have 1 times 2 times 3 times 4 all the way up to n minus 1. So I'll have n to the n minus 1 times n minus 1 factorial. So can I simplify that? There's a nice little simplification I can do in here. How do I turn this into an n factorial? Good. I'll get n to the n minus 2 times n factorial. Right? Did everyone see that? I just take one of the n's here and pop it into the factorial, right? Is everybody good on that? Questions so far? Makes sense. Okay. So this is one way of counting the number of ways I can make a directed rooted tree. Okay. I figured out what went wrong over here. So let's circle back to this one. Okay. Here we're starting out with a directed rooted tree. Okay. So this one already has the arrows in it. That was my mistake. Okay. So that's better, right? So what I'm going to do is sort of restructure this tree so that it's straight up and down. It'll be easier to see. So I have 3 guys coming off like this, and 2 of them go to forks, and 1 of them goes to a single. So a fork, and a single. Right, because this direction I have a fork coming off, this direction I have a fork coming off, but this direction I have a single coming off. Does everyone see that these two are isomorphic? Does everyone see that? Yep, cool. Okay, so this is my tree. I'm starting with a directed tree. One of the t sub n, right? This is a tree, a directed tree on n vertices. So I'm starting with one of those. I pick one of the n vertices to be the root. So I picked that one, right? So that's my root, right? And then add the n minus 1 edges in any sequence. Because remember, what I'm counting here is how many ways can I build this thing? Not how many of them are there, but how many ways can I build it? So I'm starting with one of them, right? This is just an example, but I started with this one. And now what I have to do is I have to pick what order I'm going to add in the edges to build it, right? And each time that I add an edge, I'll cross it off. Or maybe I'll highlight it. How about that? So let's say I start with this edge, and then this one, and then this one, and then that one, and that one, and that one, that one, and that one. So that's one of the ways, one of the sequences that I could use to build this tree. Does that make sense? People happy with that? Should I do another example? Another, please. Sure. Let's do this. Let's start with the same tree, but let's pick a different root. Okay. So let's say that this time I pick this root, and I'll box it instead of circling it. Okay. Although I guess that's going to have to change the direction of that arrow. That's a little unsettling, but I'm just going to roll with it for now. Okay. So I'm going to start with this one. It's going to have to change the direction of that arrow, but that's okay. So I'm going to start out with this one. It's going to have 2 guys coming off the sides. Here's my little box, right? And from this one in the middle, goes down to this guy. Now I have on the one side a 2-link chain, and on the other side 1 link and a fork. Okay. So basically, as you move, what determines the direction of the arrows? Let me just say this. What determines the directions of the arrows is moving away from the root. That's really all that determines which way the arrows are going. It's just the further you move away from the root, that's which way the arrows go, right? And of course, these two trees are different, right? I mean, obviously you can see these are non-isomorphic if you pick a different root. So I picked a different root. Now what I'm going to do is decide what order to add the edges in, right? So let's say I do, you know, all, because remember, this is the tree that I'm going to build, but I haven't built it yet, right? I need to determine what sequence, what order I'm going to add in the edges, right? Because I'm wondering how many different ways can I build these. So I start with that one, and then I do that one and that one, you know, whatever order you want. Doesn't matter, okay? Well, it matters, but any order is available to be used, okay? So, you know, so if I was to label these, right? 1, 2, 3, 4, 5, 6, 7, 8, right? I could do any order to add these in. I could add them 1, 2, 3, 4, 5, 6, 7, 8, or I could just as well add them in order 8, 1, 7, 2, 6, 5, 3, what did I miss? 4. Right? So if I was to do that, let me show you how that would look. So I'm going to start out with my vertices like this. So first I'm going to add in edge 8. My root was already picked. Okay. I'm going to add in edge 8, then I'm going to add in edge 1, then I'm going to add in edge 7, right? Then I'm going to add in edge 2, then edge 6, then number 5, then number 3, then number 4. Right? So I'm counting the number of different ways, sequences that I can build these trees. Does that make sense, Calico? Does that help? Yes, very nice. Yeah, of course. Do other people have questions? Okay, so we're almost there. We're almost done, right? I started with a tree, T sub n, and then I picked one of the n vertices to be the root. And then I added the n minus 1 edges in any order. And I want to count how many total ways there are of doing this. So I'm going to start with one of my trees, T sub n. Okay. And then I'm going to pick one of the n vertices to be the root. So what do I do to my formula here? So I started with a tree, and I'm going to pick one of the n vertices in that tree to be the root. So what do I do next for my formula? Times n. Very good, right? Because I have this tree, and I pick one of n choices, and then I add n minus 1 edges in any order. So what's the last part? Good. Times n minus 1 factorial. Right? So I pick the tree, and I pick the root, and I add the edges in any order. And this gives me two distinct formulas for the number of ways to build that tree, the different sequences I can use to build that directed tree. And since these are two formulas that are equal to the same object, the number of ways I can build the tree, I set them equal to each other. So T sub n times, and if I combine these, I get n factorial, right? Equals n to the n minus 2 times n factorial. These guys cancel. And of course, I get the number of directed trees is n to the n minus 2. What do you guys think? Pretty slick, right? Questions? Okay, so the reason I wanted to mention this is for a couple of reasons. Okay, so first of all, it's using a combination of the ideas from chapter 9 and the ideas from chapter 10. And as you, I'm sure you can guess, that's going to be what the questions on your final exam are like, right? It's going to take the ideas from multiple different chapters and combine them together into a single question. Now, the questions on your final won't be as complicated as this. That's a toughie, right? But I did want to give you, an example to show you the kinds of things that we're going to do, combining these totally different areas of thought together to prove something, right? That's sort of the whole point of mathematics, right? Is to take these different ideas and combine them to show something new. Speaking of which, I stole this. Well, and everything that I'm teaching you in this course has been stolen. Someone else thought of it already. I haven't taught you any original mathematics that I've come up with in this course, which is fine. But I did want to give you a source. So there's a really interesting book that I would recommend you read if you have some free time over the summer, called Proofs from the Book. And it's one of the authors was this guy named Paul Erdos. Write that for you. I can't do an umlaut on here, but it's there's two dots over the O. Okay, so Paul Erdos was the most prolific mathematician of all time. He had over 5,000 published papers in his lifetime. That's not like scribblings. Those are papers that are published in mathematics journals. And if you do the math on how long, he lived to be really old, but if you do the math on how many papers that is, that's more than one per week. So this guy was publishing a math paper in a journal more than once a week for like, I don't know, 50 years or some 40 years, something like that. Just crazy, right? So obviously a very talented mathematician. And he put together this compendium called Proofs from the Book. So him and his math buddies like to joke around that God has a book of all the best proofs in it, because some proofs are really beautiful and other proofs are really gross. Okay, and this is one of the beautiful ones, right? And so Erdos and his buddies would joke around that God keeps this book with all the best proofs in it that he likes to read in his spare time, right? And so what Erdos and there was another author, I forget the other author's name, but they put together this collection of the most beautiful proofs, and this is one of them, right? In the book, they actually have 4 different proofs of Cayley's theorem that all have different strategies, that all use different ideas from various different parts of mathematics. And just for this particular example, they have 4 different proofs. Most of the time they just have one version, but for Cayley's theorem, they have a bunch of versions just to show you like the really different parts of mathematics you can use to prove this thing. And yes, hell would be muddling through the worst proofs. Yes, that is the usual case for mathematicians, is making a terrible proof or reading someone else's terrible proof and muddling through it. And hopefully, if you're lucky or talented, or probably both, you can come up with a more elegant way of proving something, right? And a lot of the times that's the game. It's not proving something new. It's proving something that's already been proven, but in a nicer way. And the insight that gives you many times allows you to expand on the ideas that went into that proof in the first place, and then prove something new, right? So it's not just a kind of a goofy exercise that's pointless, right? When you prove something in a more elegant way, oftentimes that leads you to developing new ideas in mathematics. And so if you have some time, I would highly recommend giving Proofs from a Book a glance. If you're not that invested, you can definitely like download it for free online, but don't do that. But I guess Erdos is dead, so he doesn't care. His estate would be mad. But if you want to just give it a glance, I would recommend it. Or go to support your local public library now that COVID's over, right? Yeah, absolutely. So I want to show you that one just to give you a really elegant, solid proof, because I think sort of the rest of the time through this course, we're not really going to get another chance to do a really pretty one. So I want to give you a really pretty one before our time together is over, which is quickly approaching. So there's that. Any other questions for me before we move on? Okay, cool. So in that case, let's jump back into 10 point what? Let's see here. I think, did we finish 10.6 last time? I think we may have. Maybe we should do a couple practice problems from 10.6. Yeah, we definitely finished that stuff out. Okay. Yeah, let's leave it. Let's just start into 10.7. Unless anyone has any other questions on 10.5 and 10.6 that you need help with, let me know. But otherwise, okay, then let's talk about spanning trees and shortest paths. So, and that's a great quote from Kant. So I don't know if you've seen these quotes at the beginning of the sections of the book, but a lot of them are kind of goofy, but this is a great one. Each science is a real science only insofar as it is mathematics. That's a good one. Kant's a cool guy. Actually, let me leave this here. We can just use the graph that they list. All right. So let's talk about spanning trees, right? So an East Coast airline company is expanding to the Midwest and can fly any of the routes shown here, right? And what they want to do, oh yeah, no, Kant was not a cool guy. His philosophy was cool. Yes, I agree, Sean. That's a very good point. So what's happening here is that the airline wants to be able to fly between all of these cities, but it costs a lot of money to do all these different flights, right? To go from Detroit to Cincinnati and Detroit to Louisville, right? Costs more money to do all these different ones. So what they want to do is make sort of the minimum connected shape that they can, right? So here's one example where everyone's connected to everyone else. You can get from any hub to any other hub, right? But there's not multiple ways to get to a hub. There's only one. In other words, you take a graph like this one, you keep the vertices the same, and you pick some of the edges to turn it into a tree. So it's a tree that sits on top of a graph, right? So let's do an example, right? So if I have, let me make up my own graph now. So let's say we've got this guy here. Let's do one of these. Okay. That's supposed to be a vertex. That got kind of gross. Okay. So here's a graph. And what I want to do is find a tree that connects all of the vertices together. Because remember, trees are connected, right? So I want to connect up all the vertices in the graph. And that's going to include some of the edges from the original graph, but not all of them, right? So here's an example of what's called a spanning tree, because this tree is going to span the original graph, meaning that all of the vertices are included. Right? So this highlighted section is a tree. There's no circuits, right? It's connected. None of the vertices are left out, right? And it uses only the original black edges from the graph that we started with. And that's called a spanning tree. It spans the original graph. Okay. So let me ask you this. How many different spanning trees can we make from a graph? And this one's kind of complicated. Let's do a simpler example first to practice. So let's say I've got this graph. Okay. And let's label these A, B, C, and D, right? Let's see if we can come up with all the different spanning trees that would work for this graph, okay? So, so why don't you guys, why don't we list it out like this? So for example, this would be one of the spanning trees, okay? And so that one, let's call this one CABD. Right? Okay. So can someone give me another spanning tree? Let's see if we can find them all. ACBD. ACBD. Okay, that's a good one. ABDC. ABDC. Okay, what else? ABCD. ABCD. Okay. Okay, good. What else have we got? BDCA. Okay, BDCA. So that's kind of like a U shape. Okay. An N. Well, there's a reverse N. We've got that one. Is that what you meant, Sean? Down, down, diagonal, up and down, and both up and downs in the diagonal? Okay, and Sean, you were saying DBCA. DBCA. That one we've already got. It's just in the other order. Yeah, those are isomorphic, right? Amber, you had another one. ACDB. ACDB. And that one that one's isomorphic as well. Yep. Okay, so you guys are starting to list some of the isomorphic ones. Do we have any left? Okay, David says BAC. Oh, you both got it. BACD. BACD. Okay, so sort of like a C shape. BACD. Okay, well, we're kind of at a good spot now, because now look, of the four edges, we could leave out any one of them of the edges around the square. And we've left out the bottom, the left, the top, and the right. So we've sort of gotten those four. And then if we include the diagonal, then what can we do? Well, then we can either have both of the verticals, or we could have both of the horizontals, and we have both of those guys. So have we gotten them all? What do you guys think?
So I don't know how to type this because it's not in order, but the edges AC, CB, and CD.
Okay, one more time.
AC, CB, and CD. So you can take out the two edges on the outside that aren't opposite.
Very good, right? Slick. And there's another one. A, B, B, C, and B, D, same thing, but the two opposites. Very nice. So there's also these two. Okay, cool. So do we have them all now? I think so. Okay. So it looks like we have 8 of them. Is there a way that we could count how many there's supposed to be? So what I was thinking was, so here's like, this is not correct, but here's like my train of thought. Without these ones, I had 6 of these. I had 5 edges and I'm removing 2 of them, right? So because I start with 5 edges, I have 3 edges left. So I don't think we can count them exactly, but what if we had like 5 choose 3, right? Which is equal to how much? How much is 5 choose 3? 10, right? Because we start with 5 edges, we choose 3 of them to keep, right? Or 2 of them to get rid of. 5 choose 2 is also equal to 10, same thing, right? Yeah, so sorry, yeah, you're right, Sean. I switched in the middle there. I said 5 choose 2, and then I switched to 5 choose 3, but those 2 things are equal to each other, right? So I think what we can say is the number of spanning trees is at most 10, right? Maybe we get all 10, maybe we don't. Here we have 8 of them. Why are we not getting all 10? What are the 2 that we missed? Let me ask that. Complete graph. I'm not sure what you mean there, David. Oh, well, if we had a line from A to D, that would be a different situation. So that's not quite right. Sean, you're saying if we remove AB and AC, yeah, okay. So Sean, you got the right idea there. So we can't remove these 2, right? Because that disconnects A and leaves a circuit, right? Which is not a tree at all. It's not connected and it's got a circuit in it. So that's bad. So we can't remove A, B, and AC. We also can't remove BD and CD for the same reason. If we remove these 2, then we'd be left with the upper triangle and D would be isolated, right? So out of these 10, 2 aren't going to work, right? Which gives us a total of 8, which we've listed out here. See the relationship between the choose notation and the spanning trees we can come up with? Does that make sense? It's not perfect, right? Because there are these examples that sort of screw everything up, right? But there is, if you account for the screw ups, then we can get the right answer, right? Does that make sense? Any questions? Makes sense. Very nice. Okay, cool. So let's not actually count the spanning trees here. Now that I've done this one, I think there's going to be like 70 of these or something. So we're not going to go there. Let's not worry about that. Instead, let's talk about minimum spanning trees, right? So for a minimum spanning tree, you have to have labels on your edges, numeric values on your edges, okay? So for example, in your book, they have this situation. And oh man, okay, I'm gonna try to be slick here. It's gonna be terrible, but I'm gonna try. Oh man, I do not have enough hands for this. Okay, let's try one more time. Okay, if I can. Oh, wait, here, I can do it this way. One moment. There we go. Okay. Oh, it doesn't update now. Ah, dang it. Dang, I thought that was going to work. Okay. I have to arrange this just right. Ugh, okay. I give up. Do it a different way. Sorry. Zoom lectures are so hard. Here's what I'm going to do. Boop, boop. This will work. All right, looking for 703. Down here. Parse tree. Okay, yeah, we're almost there. Oh, I did it again. Darn it. Almost there. Okay. There it is. Cool. All right, awesome. We got there. Whew. All right, cool. So let me bring up my chat window here. Ugh, Zoom lectures, just terrible. I can't wait to get back on campus. Okay, so minimum spanning tree. Here's what we're gonna do. We wanna make a spanning tree over the shape, and as you can tell, there's lots of cycles on here, so there'd be lots of different spanning trees we could make. But we want the minimum spanning tree, okay? And by minimum, what I mean is when you add together all of the numbers associated with these edges, and of course these numbers are just like the distances in these cities, right? So it's like 695 miles from Minneapolis to Nashville. It's 151 miles from Nashville to Louisville, and so forth, right? And what I want to do is I want to put together a spanning tree so that we can still get from every city to every other city, maybe by multiple hops, but by some amount of hops, it's connected, right? So we can get from any city to any other. But I want to go the minimum distance between every pair of cities, okay? So how do you think we can find the spanning tree that will give us the minimum distance between every pair of cities in our tree? Thoughts? Between every pair is the lowest total. So because remember, I'm not going to include every pair, right? Because then it wouldn't be a tree, because then I would have circuits, right? So if between every pair that are in the tree, it's the minimum, that would give me the lowest total. Does that make sense, Sean? Yeah, okay, cool. So how do I go about finding them? We got two different options here, named after a couple of dudes from the 50s, Kruskal and Prim, right? Which is kind of funny because Kruskal looks kind of Kruskally and Prim looks pretty Primly. Their little pictures are in the book, so it's easy to tell them apart. Choose the smallest edge which doesn't create a circuit. Perfect. Okay, so what is the smallest edge in here that doesn't create a circuit? I'll go over it in red here. Okay, 74. Yep. Okay, so we'll throw this one in. 83. Throw that one in. 151. Okay, so we're throwing in the smallest ones that don't create a circuit. So what's the next smallest one? 230. Okay, that's the next smallest one. That doesn't create a circuit. What's next? 242. Okay, that doesn't create a circuit. Oops, wrong one. 242. Okay. 269. Okay, that doesn't make a circuit. Good. And then the only city that we've left out. Oh, 262. Ah, very nice. Okay, 262 is what we should have done. That's just slightly shorter from St. Louis to Chicago instead of Louisville to Chicago. Okay, and then the only one that we've left out is the mini apple, right? So 355, right? Even though the next smallest one is 269, that would make a circuit. It would make a big triangle, which of course is not allowed for our tree. So we can't put that one in. So we go up to the next one, 306. Well, 306 would also make a circuit, so we can't put in that one. And after that, then we have 355. And at that point, we've connected up all of the cities, so we're done. What do you guys think? In the red is our minimum spanning tree. Does that make sense? Any questions? Okay, so which algorithm was that? Was that Kruskal or Prim? Kruskal, yep. Yep, so that one's Kruskal. Prim works in a different way, okay? So does anyone have any questions on Kruskal before we move on? It's pretty straightforward. You go through the edges from smallest to largest, adding in every edge that doesn't make a circuit until you hit every vertex, and then you're done, right? Pretty easy, I think, right? Any questions, though? Maybe we should do another example. Would that be helpful? Maybe let's do one more example before we move on to Prim. Okay. Let's do, is there a more complicated one? No, there's not. Okay. Yeah, let's do this one. Oh, yeah, sorry, that's in the book. I need to get it from the file. Okay. There we go. All right, great. So here's another example. Let's try doing Kruskal one more time. So where should I begin? (1.1). So now instead of the Midwest, now we're in the Southwest. Oh, 0.8. Okay, so that one should have come first, but that's okay. Okay, 0.8, 1.1. Okay, and what should come next? 1.2. Okay, Phoenix to Albuquerque, that's a 1.2. Okay, and then 1.5, Cheyenne to Salt Lake. 1.6 would come next. Do we put this one in, Salt Lake to Denver? No, because it would make a circuit. Good. Okay, so then what comes after 1.6? Not 2.2. There's another one we can throw in first. Yeah, 1.7. Denver to Amarillo. And I think now we're done, right? Because I think we've got all the vertices and we've done the minimums. Is everyone good with that? Questions? Got it. Okay. Not too hard, right? Prim is a little bit harder, but it's not terrible. Okay, so let's try Prim's algorithm. Can someone describe Prim's algorithm to me, how it works? It's kind of complicated if you want to hop on the mic. Okay, so yeah, you do begin at a specific vertex. Choose the smallest weight from the vertices you visited. Well, what do you mean by visited exactly? And Nathan, does it matter which vertex we start at? So there's a question for each of you there. Does it matter which vertex, and what does visited mean? Okay, yep, and that's right. So you can start at any vertex you want. It doesn't make a difference, right? Okay, so that's that. And then Natasha, if you start at Chicago, Milwaukee, you choose the smallest weight from either of those places. Okay, not exactly. So rather than being centered on edges, instead you're centered on vertices. So you're not talking really about visiting the edges, you're talking about visiting the vertices. And in order to do that, it's not the ones that you visited, but the ones that you could visit. So for example, so let's start at Chicago. Let's say Chicago is our starting place, right? So I'll just put a little red dot there. Okay, so we're going to start at Chicago. And rather than thinking about the edges, we're going to think about all the vertices we could visit. So we could go to Milwaukee or Minneapolis or Louisville or St. Louis, right? And so from that, you want to pick the smallest weight to any of those places, right? So which edge would I add? Milwaukee, great. Okay. Now I'm going to repeat that same thing, but now instead of Chicago being my only starting point, now I can start at Chicago or Milwaukee. So the possible edges I may be able to add include all the ones connected to Chicago and all the ones connected to Milwaukee. So any of the yellow ones, right, could be possible edges I could add, and which one should I pick? $262, yeah, to St. Louis. Very nice. So to St. Louis is the one that I add, right? So now I've got Milwaukee, Chicago, and St. Louis all covered. And now let's put all the possibilities back in. So now I could add in anything from St. Louis, anything from Milwaukee that isn't accounted for yet, or anything from Chicago that isn't accounted for yet. Okay, so which one should I put in next? 242, right? St. Louis to Louisville. Very nice. I'm just going to draw over it. Hopefully that'll work. Yeah, close enough. Okay. Now my possibilities include all the exits or all the edges adjacent to Louisville, right? Which is going to include 306 and 151. And I'll just go along with your answer there, Nathan, because you're absolutely right. We're going to throw in the 83 Louisville to Cincinnati. Or Cincinnati, as my buddy from there likes to say. Okay. Now I throw in the 151. Yep. And then? And then the 230. Yep. And lastly, the 355, Chicago to Minneapolis. Good. Oop, oh, my computer died. Okay. There we go. And we come out with the same picture we got before, right? What about 242? What about it? This guy here? Never mind. Okay. Oh yeah, that's it. Yeah, that's the other one. Yep. Cool. Yeah, I was confused by that the last time. Yeah. When you create weighted graphs, this is called a weighted graph, by the way, because each edge has a weight associated with it, like, like the weight of a bag of apples, okay, the heaviness of it, okay? So these weights here aren't about heaviness necessarily. They're just about, it's more about like cost, right? Because the reason why you weigh a bag of apples is to know how much you have to pay when you get to the cash register, right? And so these weights here are a cost that's associated with walking down that edge. So if you walk down the edge from Minneapolis to Nashville, you'll be going the cost of 695 miles, right? And weights can mean lots of different things. It could be a distance, it could be a literal financial cost. It could be the amount of gallons of fuel that the airplane has to use to get there. There are lots of different things that the numbers could represent. But all of those things really boil down to the idea of a cost, right? Because whether you're thinking about distance, or you're thinking about actual money, or you're thinking about the amount of gas it takes to get there, really what that all boils down to at the end of the day is money, right? The farther the distance, the more gas you have to use, the longer it takes for you to get there. And of course, time is money, right? And so really the idea of a weighted graph is really coming down to the idea of cost, is sort of a good way of looking at it. And so when you have a graph with these, numeric values attached to the edges, what you should be thinking about is those numbers are associated with some kind of cost, right? Does that make sense to people? Good with that? Makes sense. Cool. Okay, so let's do the same thing on this one, and this time I'm going to let you guys do it. So what vertex should I start at? Denver. Okay, so we'll start at Denver. Great. And from Denver, I have lots of options, right? So let me put in my options here. My options are to Salt Lake, or Cheyenne, or Amarillo, or Albuquerque, or Phoenix. Remember, it doesn't matter where you start. You're going to get the same graph out either way. Right, so those are all my options from Denver. Which one am I going to pick? 0.8 to Cheyenne. Very nice. Okay. So now, what am I going to update in terms of my possibilities of where I could go next, my yellow lines? What do I need to put in there? Got to update my yellow lines. And which ones do I want to put in? 1, 5, and 1, 8. Perfect. The new options from the newly connected vertex is going to be added to my list of possibilities, right? Okay. So now here's all of my possibilities that I could put in. So which one am I going to pick? The 1.5. Very nice. Cheyenne to Salt Lake. That's the minimum out of my list of possibilities. Okay. Now, which additional possibilities do I need to put in? One, 9, and 2, 5. Which possibilities do I need to take out? Oops, wrong color. Yeah, I put in the 1, 9 and the 2, 5, right? But I take out the 1.6. right? Because I'm not allowed to make a new edge between two vertices that I've visited. I can only make an edge between a vertex that I have visited already and a vertex that I haven't visited yet, like Amarillo, for example, right? So I could put in Denver to Amarillo, or I could put in Cheyenne to Amarillo, or Salt Lake to Phoenix. Any of those are fine, but I can't go Salt Lake to Denver, right? And the reason why we're sort of expanding outward and making this group of vertices that we've already visited is to avoid making cycles. That's the whole point of doing it that way, right? So 1.6 is not going to happen because we can see that both of those um, cities we've already visited. So I'm going to get rid of this guy. Okay, perfect. So now what do I do? (1.6). So that's from, oh, nope, we can't do 1.6 because that's the one we just took out. Or maybe that's the one you were saying we should take out. Sorry, which one do we do next? Sorry, Natasha, I think you said that a while ago. 1.7. Okay, Denver to Amarillo. Nice. Yeah, it's hard because in the chat, it doesn't automatically list the time that someone said something. I have to go scroll over and look at when you said it. It's kind of annoying. Okay, so fine. So now what new edges do we put in and what edges do we take out? Add 1, 1, take out 1, 8. Very nice. So we'll add 1, 1, and we'll take out 1, 8. Cool. Okay, so now what do we do? We do 1.1. Yeah, very nice. Okay. Okay, so what do we add? What do we take out? Add 1.2, take out 2, 2, and 2, 5. Okay, so we add 1.2 as a possibility. We take out these two, 2, 2, and 2, 5, because those connect two vertices that have both been visited already. Take out that one and that one. Okay, great. And the last one that we want to add? (1.2). Sweet. And there's Prim for you. Questions? Okay, and let me ask you a question. Of these two algorithms, Kruskal and Prim, which one do you think is easier to do by hand? Kruskal. Okay, sure. I agree. I think Kruskal is easier as well. Let me ask you another question. Of these two algorithms, which one do you think would be easier to program and why? Prim rather than Prin. Okay, you think Prim. Why? Why is that, Nathan? And I agree with you, but why is that? Okay, Lucas, you said Kruskal because of your data structures. Okay, so that's interesting. So Lucas, what about your data structures makes Kruskal easy? You don't have an easy way of getting edges for a vertex. How are you representing your graph there, Lucas? A set of vertices and a set of pairs of vertices. Oh, okay. That's interesting. So in that case, yeah, I guess that makes sense. Let me say that that's not the best way of representing your graph in the first place. I think a better way would be to represent your edges rather than as a set of pairs of vertices. Instead, for every vertex, you have a set of other vertices that it connects to. Does that make sense, Lucas? So here, let me do a little example. Okay, so if you wanted to, oh yeah, yeah, not that you should change it. Yeah, no, don't change it. But just in general, there's sort of two good ways of representing graphs. And your way works, it's just not the best way. So I guess there's three ways, but your way is not as nice. And here's the reason why. So let me start with an example, and then I'll tell you why. So for example, this one, I can just use, let me do it this way. I'll just use first letters, okay? And I'll go alphabetically. So AL would have the set Amarillo, Cheyenne, Denver, Salt Lake, and Phoenix, right? And then we would go Amarillo. And that would have Albuquerque, Cheyenne, and Denver. And then we would have Cheyenne, which would have Amarillo, Denver, and Salt Lake. Then we would have what next? Denver, which would have all five, right? AL, AM, C, P, and S. Then we would have Phoenix, which would have Albuquerque, Denver, and Salt Lake. And lastly, we would have Salt Lake, which connects to Albuquerque, Cheyenne, Denver, and Phoenix. So does that sort of way of encoding edges in your graph make sense to everybody? There's a name for it. It's called an adjacency list for obvious reasons, right? You list out all the vertices, and for each vertex, you have a list of the other vertices that are adjacent to it, right? So if you wanted to put in weights, then I think each one of those entries in the list would be a pair, where you would have, for example, AM would be, AL 1.1, D 1.7, and Cheyenne. Oh, okay, good. Whew, almost lost it. Cheyenne 1.8. So it looked kind of like that. Does that make sense, David? Yeah, cool. Yeah, so and Nathan, that's where I'm going with this. So yeah, so you're absolutely right. I agree with you, but let me get to that in just a minute. So if you have an adjacency list like this, where you have, who's connected to who, then I think it would be a bit easier to set up Kruskal, or prim rather, which is what you were saying there, Lucas, right? You didn't want to do prim. So I think if you had it set up this way, with the adjacency list, prim would be a bit easier because you would have an immediate list of who is connected to you, and all you would do is take out those items that each vertex connects to and throw them into a list, a sorted list. And from that sorted list, you would just take out the minimum from that list each time. And that would be the new edge that you add, right? You would have to be careful, though, each time that you add an edge to your list to make sure that you're not connecting up to a vertex that you've already seen. So you would have to keep an additional list of the vertices that you've already seen. So really, in order to implement prim, you need two lists. You need one of the vertices that you've actually been to, that are actually in your tree so far, and another list of possible vertices you could visit next, along with the edge weights for those, right? And so once you visited a vertex, you would have to go through your list of possibilities and delete all of them that connected to that one that you just went to, right? And then to find the actual one that you go to, you sort your list of possible vertices to visit, and then pick the minimum one, right? Now that's called a priority queue, is the name for that list of possibilities. So the list of possibilities, you would use what's called a priority queue, where the one that has priority would be the smallest weight. You already had a pathfinding function implemented to avoid creating circuits. Okay, well, so Lucas, so now let's center on that, right? So Lucas, you already had the hard part done for Kruskal. Now Kruskal is easy for humans with eyeballs because we can see what's going to make a circuit and what's not, right? So if I, let's go back to this other example here, right? It's really clear to me that if I put in Chicago to Louisville, I'm going to be making this triangle. And so, so I won't put that one in, right? For Kruskal. Let me actually undo this and let's go back to Kruskal. So I put in 74 and then 83 and then 151 and then 230, I think is next. Yep, 230. And then the next one would be 242, 262. And then when I try to put in this 269 here, it's clear that that would make a circuit. So I won't do it, right? And that's easy for humans to see with their eyeballs. But that's not easy for a computer to see, right? Because what you need to do is you need to make a function that decides whether or not an edge that you put in is going to make a circuit. And how would you do that? And so Lucas, since you've already done that, maybe you could explain, how could you make a function that would decide whether or not an edge that you're adding makes a circuit? Depth first search. Okay, so DFS stands for depth first search. What does that mean? Can you explain that? Might be better to hop on the microphone if you can. It's kind of complicated.
Okay, so I explore every path possible by I go to path A and then I go to the next path all the way, trying to find the goal. If I end up stuck, then I go back a path, try to go the other paths that more back path can connect to. And it will get a solution, but it's not necessarily the best solution.
Okay, so let me see if I can repeat that back, and let me see if I got it right. So from some starting point, you check to see every possible path that you could take. Is that right?
Yeah.
Okay, and then on the way, how would you know if you've hit a cycle?
I mean, you'd have to probably have a list of vertices you've already hit.
I'm sorry, can you say that one more time?
You probably also need to have a set of vertices that you've already touched so you don't go back.
Good, that's exactly right. So you explore every possible path. you have a list of the vertices that you've seen so far on one particular path that you're looking at. And as you're going down this possible path, if you hit a vertex that you've already seen, that you've already visited, that means you have a cycle, right? Now that's going to be not that hard to implement, but kind of hard. I mean, there's certainly lots of possibilities, right? So if we start thinking about every possible path here, let's do it color-wise. Let's do Roy G. Biv. All right, so if I think out of every path out of Chicago, well, so I have these options at first. Right? So there's my first options out of Chicago. That's the first layer of my search. Okay, I'm searching for all the through all the possible paths. Right? The next layer on my search is going to look like this. Well, that's all the places I can go from these guys. So there would be this one. Where can I go from Minneapolis? Where can I go from St. Louis? Where can I go from Louisville? Because Louisville is connected to this red one, so I can also leave anywhere from Louisville. And in 2 steps, I can hit all the possible paths. Well, almost all of them. In the 3rd step, I would get Detroit to Cincinnati, right? And a nice way of thinking about depth first search is to arrange it like a tree, right? So let's see, can I, here, I'm gonna switch back over. Here we go. All right. Maybe I should do this side by side. That'd be easier. Maybe. Okay, let's give it a try. Squish that guy. Okay. So here's what I've got, right? I'm going to start at Chicago. And what I'm going to do, actually, is I'm going to build a tree out of this graph. So I'm going to start at Chicago, right? And where can I go from there? Well, I could go to Milwaukee, Minneapolis, St. Louis, and Louisville. Right? Where can I go from Milwaukee? Well, from Milwaukee, assuming that I don't go back to the one that I started at, right, to Chicago, then I could go to Louisville. Right? From Minneapolis, I could go to Nashville. From St. Louis, I can go to Louisville. And from Louisville, I can go to Milwaukee, Detroit, Cincinnati, or Nashville. See how I'm building this tree? Does that make sense to people? And then, of course, I could keep going, right? Do people follow this? Does that make sense? I'm like listing out all the possible paths, right? Yes. Okay, cool. So what I want to do is, in order to do Kruskal, I have to build this tree, right? And then look and see, okay, as I follow this tree, find the edges that are already there, find the edges that I'm gonna add, and then see if there are any repeats to a place that I've already visited, right? So as I go down the tree, right, I if I add in this new edge, is that gonna take me back to Chicago? Right? So if I go to St. Louis and then to Louisville, well, Louisville, one of the things that it connects to is back to Chicago. So if I take this path, that's not allowed, right? Because Chicago's been visited twice, and that's how I know if I have a circuit, right? So it is a little bit complicated. And the nice way to do this is to use a recursive function to do it, right? Which sort of makes sense, right? Oh, that's more of a breadth first search. Yeah, I suppose you're right. That is a breadth first search, Lucas. I agree. I misspoke. So you were doing a depth first search, which, let's see, is that what we want? Well, you're going to build the same tree either way. The question is how you traverse the tree, right? So maybe I should talk about this for just a moment, okay? So there's two kinds of searches, which are graph searches. Well, there's probably more than two, but there are more than two. But we'll just talk about these two for now. So there's breadth first search or depth first search. Let me write those out, depth, breadth. Not depth and breadth, right? Depth and breadth, right? And the difference is how you explore this tree. So breadth first search means for each node, you look at all of its children. And then for all of those children, you look at all of those children. For all of those, you look at all of those children. So you're sort of looking like one level of the tree at a time. That's breadth first search. Depth first search means you go all the way down one line, right? And then you come up and from the very bottom of the tree, you come up one level and then check from that, right? All the other ones there. Then you come up from that level and check all of those from there, traversing all the way back down the tree for all of those options. So in breadth first, you start at the beginning and you take each level one at a time. Depth first search, you go all the way deep down the tree. That's why it's called that, right? Instead of being broad, like each level gets really broad really fast because it's going to grow exponentially, right? So it gets broad very quickly. Depth first search, you go all the way down to the bottom, and then you sort of build the subtrees coming upward. So you're going very deep down the tree. Yeah, so for many of you, that's probably the first time you've heard about these, which is fine. We're not even going to learn about them in this class. I just wanted to mention them. This is something that you'll learn about in your, in your 300 level algorithms class when you go to Portland State or OSU or wherever next year. In your algorithms course, you'll learn about these guys. And so that's what makes Kruskal difficult, is that you have to implement a search like this in order to decide if you've already seen a city before, right? Which kind of makes sense when you think about it, right? Like if I come over here and I'm adding these edges in, I added in 74, 83, blah, 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 Chicago to St. Louis and Louisville, and I want to know, can I add in 269? Well, what I have to do is I have to look at all the different ways I can get out of Chicago. And then from there, all the different ways I can get out of those cities. From there, all the different ways I can get out of those cities, and keep doing that over the entire graph that I've made to see if putting in 269 is going to make a cycle or not, right? So you have to do all the possibilities of all the possibilities of all the possibilities, et cetera, et cetera, et cetera, right? Which I think in this case is going to be a breadth first search rather than depth first, but I'd have to think about that, Lucas. I'm not sure which one would be more appropriate in this case. Okay, I think another solution for this is to choose the shortest way. Nathan, say more. I'm not quite sure what you mean by that. Just gonna move this while you're thinking. Okay, you're coming up with a different way to do, you're coming up with a different way to find the minimum spanning tree. Is that right, Nathan? Yeah, okay. And so your idea is choose the shortest way, add the two vertices of that edge into a known set of vertices. Okay, and you think you can avoid doing the depth first search that way? Okay, let's give that a try. Let's see if that works, right? So if I pop over to, let me turn this off, turn this on. Okay, so let's undo this real quick. Okay, get my chat window back up. Great. It's just the beginning. Then we find that, yeah. So you would repeat steps 1 and 2. Is that right, Nathan? So 1 and 2 are sort of in a loop until you run out of vertices. Is that right? And 2 has a condition, sure. Yeah, right. I got it. Cool. Okay, yeah, let's try it. So, so step 1 is choose the shortest way. Okay, which would be Milwaukee, Chicago. Then we're going to add those 2 vertices into a known set of vertices. Okay, which is going to have Milwaukee and Chicago. Okay, and then what do? Then we find the next shortest way and add those ones in. Is that right? So then we would add in, not yet. Okay, so what do we do next? We have to check the vertices of that edge. Oh, to make sure that there's not a cycle. Is that right? If one vertex of the edge isn't in the known set, it's accepted. Ah, okay, sure. So of the new edge that we're adding, one of them needs to not be in the known vertices set. Okay, let's see if that works, right? So we would then add in Cincinnati, Louisville. Neither of those are in Milwaukee, Chicago, so we're good on that. Ah, okay, so Lucas, you already tried this. Interesting. And you sometimes end up with a disconnected forest. Okay, well, let's try it on this graph and see if we get a tree or a disconnected forest. Let's see what happens. All right, so I'm going to add in now Cincinnati and Louisville. Okay, then what am I going to add? So the next one would be 151, which is okay because 151 only has one of the vertices in the known set, Louisville, but Nashville is not in the known set, right? So now I would add one more to the known set, which would be Nashville. Okay, so now what happens? So now we would do 230, right? Is that the, yeah, that's the next one, 230, right? So I put in 230 and I add Detroit to my list of known vertices. Oh, it does create a forest, huh? Okay. And then what do I want to do? Yes, because once I try to put in Chicago to St. Louis, which is going to happen in just a minute, right? So right now, my next one that I want to put in is St. Louis, which is fine because that has one of them not known yet, right? St. Louis is not known yet, so that's fine. I add that to the known list. Right? But now I'm in trouble because now I want to add in Chicago to St. Louis, but those are both known already. Yeah, so it's going to make a forest rather than a tree. Yeah, so unfortunately that won't work. Yeah, it's a good idea though. You're close. So I think so what you've done is kind of a combination of Kruskal and Prim, but unfortunately it's not guaranteed to give you a connected tree at the end of the day. Cool. Okay. Yeah, that was a good experiment. That's great. This is absolutely what you should be doing. So Nathan, that's great. Even if your ideas don't work out at the end of the day, the whole point of this is to try to think of new algorithms and new ways to attack problems like this that are going to be easier to program, faster, right? Easier to understand, whatever, benefit this algorithm has. And you should definitely be trying to come up with your own algorithms and see if you can figure out nice ways of doing this. And, in some sense, that's really what being a computer scientist is all about. It's about coming up with good algorithms. That's not what being a programmer is about. You can be a programmer and just make websites, and that's fine. You don't care about algorithms. But being a computer scientist, I mean, this is kind of the game, right? Cool. Okay, so why don't we take a break here? Let's take 10 minutes, and then we'll come back and talk about Dijkstra's algorithm, which is the shortest path algorithm. and talk about our lab for this week. All right, so let's take 10. I'll see you soon. Okay, so before we jump into our last algorithm, I remembered that I didn't tell you the other way of representing a weighted graph besides the adjacency list. So I showed you that adjacency list as one way of representing a graph, be that a weighted graph or unweighted, directed or undirected. It works for any of those. But another way of representation, which we actually talked about a little bit already, is an adjacency matrix, right? So for an adjacency matrix, there's a nice way of doing that with a weighted graph. Let me show you here how that could work. Here we go. So here we go. Okay. So for this adjacency matrix, what I'm going to do is come up with, no, this one's a little too big. Let me make a smaller one. Do an easier one here, actually. Let me do my example that I did here. So let's do this guy. All right, so here's A, B, C, and D. And let me put some weights in here. So maybe this is 5, 10, 3, 1, and 8. Right? So for my adjacency matrix, remember the way that that works is I make a matrix whose size is in both dimensions equal to the number of vertices. So it's going to be 4 by 4. Okay, so I'm just putting, you don't have to put these on, but this just sort of makes it kind of clear what goes where. Now from A to A is weight 0. You're already sitting there, so you don't have to go anywhere to get there, right? From A to B is 5, and from B to A, of course, is 5, right? From A to C is 10, and from C to A, of course, is 10. From A to D is infinity, because there's no connection between them, right? So let's see if you guys can fill out the rest. So what's the weight from B to B? 0, okay. From B to C? 3, great. And from C to D? 8, excellent. Okay, how about from C to B? C to, B to D. I'm sorry, B to D is, well, so the reason why is it's 0 instead of infinity, even though there's no path, is because rather than thinking about whether or not there's a path. Well, think of it this way. If you're thinking about cost, how much does it cost to get from node B to node B? It doesn't cost anything because you're already there. Does that make sense? Yeah, cool. Okay, and I did find a mistake. From B to D is not 8, that's C to D. What should, yeah, that should be a 1, right? Let me change that into a 1. All right, so that one should be a 1, okay. How about from C to B? What do we have here? 3, nice. Okay, C to C? 0. And C to D? There's our 8. So 8 should have been there. Okay. B to D, or sorry, I guess D to B. 1. Okay. C to D. 8. And lastly, D to D, 0. Right. So there's another nice way of representing a weighted graph with a weighted adjacency matrix, rather than the other adjacency matrix, which was counting up how many paths there are. this, instead of counting how many paths, is showing you the weights of the paths. And you could certainly use a data structure like this, just a two-dimensional array, right? You could use this instead of a list of pairs that we were talking about before for the adjacency list. And I think either way is a nice way of representation of a graph in your program. Is everybody happy with this? Does that make sense? Questions? Makes sense. Cool. Okay, so in that case, let's go into our last algorithm today, which is Dijkstra's algorithm. The nice way to remember how to spell Dijkstra is it has an IJK in it, right? IJK, letters all in a row. So it's easy to remember how to spell it. Stra. Right. And his algorithm is for the shortest path. Cool. Okay, so what we're going to do is we're going to start out with a graph. I'm just going to copy it from the book. So I've got a hexagon. Okay, and in my hexagon, I've got this guy and this guy. I'm going to label these A, B, C, D, E, Z. These are all vertices, of course. And my numbers go 3, 6, 7, 4, 6, 12. And inside is a 5 and a 2. Okay. And what I'm going to try to do is I'm going to try to find the shortest path from A to Z. Okay, great. So let me show you the algorithm, just to show you how bad it is. All right, here's the algorithm. Oh, can I even zoom out that much? Oh, I can. Okay. So here's the algorithm. I guess I can scroll in a little bit here. Okay. So here's what I'm going to do. I'm going to make T, which is going to be a tree, right, is a graph with the vertex A and no edges. V of T is going to be the vertex set of T, and E of T will be the edge set. Okay. I'm also going to make this function L, okay, where L of A is 0, and for all vertices in G except A, L of U equals infinity, where L is called the label of X. Okay. So I'm going to set up this number, this label number for all the vertices, and it's going to be 0 for our starting vertex and infinity for all the rest of them. Okay. Then I'm going to initialize V, which is a particular vertex equal to A, and F to be the set of A. Okay. So V denotes the vertex most recently added to our tree T, and F stands for the fringe. Okay. So this is all just setup, steps 1 through 3. I'm just initializing stuff. Okay. Now here's the main loop of the algorithm. What I'm going to do is I'm going to reassign F to be, remember F is the fringe. What I'm going to do is make it the set of the fringe minus the most recently added vertex unioned with the vertices that are adjacent to V and not in the vertex set. Okay, so you'll see why it's called fringe in a second when we do this example. Okay, then for each vertex that's adjacent to V and not in V of T, the ones that we just added to the fringe, I'm going to look at their labels, and if the label that they used to have, their new label plus the new weight between them is less than their old label, then I'll replace it. I'll replace their label. The label is how far away is it? right? A label is how far away is this particular vertex from our starting point A. That's what the label is meant to indicate, okay? That's why the label of A is 0, because how far away is A from itself? Well, 0, right? So what I'm going to do is I'm going to update the length or the label, I mean, you can think of L sort of either way, to be shorter, right? To be the shorter thing if I find a shortcut. Basically, this whole idea of finding the shortest path is to look through every possible path and find all the shortcuts, right? And so if I find one where my new length, my new label from the starting point plus the new weight is less than the old one, then I'll just replace that, right? Last step, find a vertex in the fringe with the smallest label, so the closest thing to get to, add that vertex to my vertex set of my tree, add the edge to the edge set, and reset V to be X. So as I'm looping around, right, V is what's changing, and V is just going to be the closest thing to the vertices that I've seen so far. And David, you had a question. What is BD? I'm not sure. Was that on this page, David, or was that somewhere else? Not sure what you mean. The weight of the line segment in the example. Ah, I see. Cool. From B to D, that's a 6. Sorry, that's hard to see. There we go. Yeah, you're welcome. Okay, so that was a lot of junk. Okay, so let's do it, and I think it'll make a little bit more sense, right? So first of all, we're going to do our setup. Okay, so we have the vertex set. Well, so basically what we're going to do is we're going to make a table, okay? And we're going to keep track of all the stuff in the table. And what I'm doing for steps 1 through 3 of my algorithm is just putting in the first line of my table. So let me show you how this table looks. I'll put in my step number, my vertex set of T, my edge set of T, the fringe, and then a list of all the labels, right? So I'm going to have label for A. I'll forget the L. It's kind of stupid. I'll just put A, B, C, D, E, and Z. Oops, crap. I screwed that up. Uh-oh. Well, too bad. I'm already making a mess. What else is new? All right, there we go. So there's my little table. And we're gonna have quite a few steps on here. The reason why we go through all this work is because finding the shortcuts is really hard in a complicated graph. So you need to keep track of every possibility of the different ways you might go in order to make sure that you find those shortcuts in the right way. It's not that hard to see what we're supposed to get here. In fact, let's do that. So what is the shortest path from A to Z in this example? Does anyone see it? ABDZ. Cool. David, you said ABEDZ. So let's look at both of those. So ABDZ, you'd have 3, 6, 7, which makes 13, 16 for this one. This one would be 8, 10, 17. So I think ABDZ is 1 shorter than yours, David. 16 versus 17, right? Does that make sense? Right. Cool. Okay. Because and the only difference is from A to D, because here we have 3 plus 6 is 9. Here we have 3, 5, and 2 is 10. So that's our difference of 1. That's where that comes from. So what I'm going to do is I'm going to set up my table. I'm on step 0. My vertex set that's included has A, and I'm going to stop doing curly brackets after this. And my edge set has nothing. My fringe has A in it, my distance to A is 0, that's the label, and the distance to everything else is infinity. I'll just draw a line, keep everything all neat here. Okay. I can zoom a little bit and see that a little better. Okay, cool. So here's what I'm going to do. Step 1. It says, the first thing that I do is I update my fringe, right? Oh, sorry, and V is equal to A. So so let's keep track. Well, I guess I'm not keeping track of V, little v. I'll just keep track of little v over here. So V, it says, is A to start out with, right? What it says is the fringe is equal to F minus V union all the vertices that are adjacent to V but not yet in the vertex set, which is called the fringe, okay? So let me say that one more time. Take the fringe minus the current vertex that I'm looking at. So the fringe, right? Minus the current vertex that I'm looking at. So I get rid of A, and I add in all the adjacent vertices to V. So what am I going to add into my fringe? B and C, right? So on my next step, on step 1, the fringe should have B and C, right? Okay, so that's step 1 of the while loop, okay? Step 2, for each vertex that is adjacent to V and not yet in the vertex set, which is both of these guys, if the weight L of V plus the weight from V to U is less than the old weight, then I update it, okay? So, oh, and I should say for the vertex set and the edge set of T have not changed. So I'm just gonna bring these down. They're the same as they were before. So this has A in it, this is still empty, okay? So sorry, I should have done that before. These are just the same as the last one. They're gonna get updated on the next step, but for the first step, they're just the same as before. Now what I'm gonna do is update all my weights, okay? So A is still 0. And now the question is the old weight of B, infinity, is that more than the distance from A to B? No. But sorry, let me say that again. Is infinity more than the distance from A to B? Yes, right. And I said it backwards, so that's wrong. Is the new weight less than the old weight is the way I should have said it. Okay, it's the same thing, but I said it kind of backward, right? So the new weight is less than the old weight, and I replace it because I'm trying to find the shortest path, minimum weights, right? Smallest weights. So 3 is less than infinity, so I put that in there, right? How about C? What should go in here? Four, very good. How about D? Still infinity, same thing with E and Z, right? Okay, so there's step 1. And I think a nice thing to do to really understand what's happening is to show you the fringe, okay? So here's the fringe. The fringe is the outskirts of what we've seen so far, right? Should we update D of U? I'm not sure what you mean by that, Lucas. So U in this case would be 3 and then 4. So I think we did update them, right? D of U equals V. So, okay, so wait 1 second. Oh. Sorry, I was thinking distance. Okay, so when L of U is changed to a smaller value, the notation D of U is introduced to keep track of which vertex in T gave rise to the smaller value. Okay, so D of U is going to be V, right? Which in this case is A. So what is that trying to tell us? Here, let me show it to you here. Okay, for each vertex U that's adjacent to V and not yet in the vertex set, which would have been B and C in our example, if the weight is smaller than infinity, which it was, then we'll update that label and set D of U equal to V. Okay. Adding V to T does not affect the labels, except those adjacent to V. When L of U is changed to a smaller value, D of U is introduced to keep track of which vertex in T gave rise to the smaller value. Okay. Our last step in the while loop is to find a vertex X in F with the smallest label. Add this vertex X to V of T and add the edge D of XX to E of T. Okay, so what is that trying to say? Okay, so to get the minimum value for B, you have to come from A is what gives the path when we find it. So D is like Dijkstra, right? It's the answer. It's the path that we're looking for, right? So there are two things that we could try to find here, right? We could try to find the weight of the shortest path, or we could try to find the actual, vertices that we go to, the actual path itself, right? Which is going to be a list of vertices where you go A, B, D, Z, or whatever it is, right? And so it looks like the D of X, those are going to be encoding the actual path that's going to be our result, right? Okay, so let's see if we can do this last step here. So find a vertex X in F with the smallest label, add X to the vertex set, and add that edge to the edge set. So what's the vertex in F with the smallest label? In other words, what vertex on the fringe is the closest to the starting point? B, right? And it says what we're supposed to do with that is add that to the vertex set and add the edge from A to B to the edge set. So here's step 2. Now my vertex set has A and B. My edge set now has the edge AB. Let me put some commas where they're supposed to go. Okay. So now when I create my fringe, right, now A is out, right? A is done, right? It's not in the fringe anymore. Now for this fringe, right, the fringe is the old fringe minus V, right? And of course, V is the new nice vertex, right? V equals X, the smallest one from before. So what is V now? B. Yes, good. Right? So now what I'm going to do is I'm going to get rid of B from my fringe and add the vertices that are adjacent to B. So now what my fringe is doing, right? My fringe extended out to B and C from A, but now B is not in the fringe anymore. And I'm going to add in those vertices adjacent to B, D and E, right? So now my fringe is CDE. See what I mean by fringe? It's sort of like moving outward from my starting point, right? And it's the boundary between the stuff I've looked at and the stuff I haven't looked at yet. That's why it's the fringe. It's like right in between the things I know and the things I don't know. If anyone's ever seen that show, Fringe, then you know what I'm talking about, right? Okay, so now what do I do? So I've updated my vertex set, my edge set, and my fringe. What's my next step? Update the weights. Okay, so what have I got? A stays, will that stay the same? Well, the next one's 3. B is 3. What about A? Still 0, right? How about C? For D, well, currently I have infinity. What's the weight to D according to my fringe? Not 6, you're close. 6 is part of it. Yeah, 9. Yeah, exactly, because I do the 3 plus the 6. And since 9 is less than infinity, I put the 9 in there, right? Okay, how about E? What have I got there? Eight. Very nice, right? 3 plus 5 gets me into E on the fringe, right? And I know that I'm doing 8 and I'm going, 3 and then 5, A, B, E instead of A, C, E. And the reason why is because when I update these weights, I'm always looking at V, right? Which in this case, my current vertex, which is B that I just added. So as I add these guys in, it's going to be, it's going to change in that way, right? It's going to change as a result of B rather than as a result of C, because that's B is my last vertex that I messed with, right? And Z, of course, is still infinity. We haven't gotten there yet. Okay. So now what I want to do is I want to find my next V, right? And so the question is, which vertex that I have not yet seen, that is not yet in the vertex set, has the smallest weight? Not E, different one. So not in the vertex set with the smallest weight. C, yeah, very good, C, right? C has 4, not in the vertex set. So what I'm gonna do is now V is gonna be my vertex C. Here's step 3. And my vertex now is A, B, C. I'm adding in my edge, AC. C is out, right? Sort of out of luck here, right? And now for my fringe, what am I going to add? And what am I going to take away? I'm going to remove C. Good. Am I going to add anything? No, I'm not going to add Z, because remember, I'm doing all the things that are available from C. C is my last vertex I've added, right? So I'm going to add the things that are available from C, which is what? A and E, right? And A we've already done, and E's already in there. So we're actually not adding anything. My fringe now is just D and E. Does that make sense? Yeah, so the fringe, it's not quite the same. We got rid of C, but other than that, it's the same. Right? Okay, so now we put in our new labels. And let's make this fun. This is kind of stupid. Let me make this do something more interesting. I'm gonna make this into a 2. So this edge is 2 instead of 6, right? Which is not gonna end up changing our shortest path. Well, maybe I should make it 3. Yeah, I should make it 3. That'll make it not change the shortest. Well, 4. Well, let's see. Now 4 is not going to do anything interesting. Nah, whatever. I lied. I'm just going to do what the book has. We'll screw around with a different example later. I'll just leave that at 6. Never mind. I was going to do something cute, but it didn't work. Never mind. That's what happens when you try to do something cute on the fly. You just end up looking stupid. So, fine. So let's put in our vertex weights. So what have we got here? So what do we got for A? Zero. B? Three. D? Sorry, C? 4. D? 9. And here's where something interesting happens, right? I could get to E in 8 steps, right? With weight 8 the last way. Now to get there, it would take 10, 4 plus 6. So what am I going to put here? Still 8. I didn't find a shortcut, right? Because 4 plus 6 is 10. That's not a shortcut. That's longer than the original path I had, right? What I was going to do is change this so I did get a shortcut and show you what a shortcut looks like, but that's okay. We'll do a shortcut next time. This is the failure to find a shortcut in this particular example. Does that make sense? Questions? Okay. Z, same as it ever was. Still haven't gotten there yet, right? And now A, B, and C are all in my vertex set. I'm going to, oh man, I'm almost out of time. Uh-oh. Okay, we should go a little faster. Out of the remaining vertices that are not in the vertex set, which has the smallest weight? So the vertices in the fringe that are not in the vertex set, which both of them are not, which one has the smaller weight? E does. E has 8, which is smaller than 9. So my next vertex is going to be E that I consider, right? So E is now out, right? And I put in the edges that are adjacent to E, which are here and here, right? So here on step 4, got my vertex set A, B, C, E. My edges, I added 2 of them. I have A, B, A, C. I've added D, E, and E, Z. Right? And now my fringe, since I've gotten rid of E, still has D in it. I've gotten rid of E. And now what else does my fringe have? Z as well. Very nice. And now let's update my edge weights. A, B, C, and E are all going to stay the same. Because, I mean, those are all done. Those are dead already taken care of them. How about D? Does D get a new weight? Now I have 3 plus 6 is 9. 3, 5, and 2 makes 10. So does D get a new weight, or does it keep the old one? Keep the old one, because 10 is bigger than 9, so I always keep the minimum. I'm looking for the shortest path, right? So I keep the smallest weight. So I again failed to find a shortcut to D, right? Now I can put in a weight for Z. So what's that going to look like? So finally, I have a route to Z, not 12, 12 plus the amount of weight that it took to get to E. Very good, so 20. Very nice. Cool. Now, almost done, 2 more steps. Okay, cool. So now, what am I gonna do? Well, now I'm on step 5. Oh, I need to find my new V, right? Sorry, I forgot to do that. So out of the things not in V, which are D and Z, which has the smaller weight of the two? Well, that would be D. 9 is less than 20. So my new vertex I'm considering is D, right? So now here I have A, B, C, D, and E. I'm going to add in any adjacent edges from D that aren't there yet, which is that one, the last edge, right? So now in my edge set, I have AB, AC, DE, EZ, and DZ. In my fringe, what am I going to have there? Just Z. Good. And let's throw in some weights, right? So of course, everything that I've done, so now D is out, right? I've looked at D and it's done. So A, B, C, D, and E are all the same. What about Z? Have I found a shortcut? Because I used to have 3, 5, 12 is 20. And now do I have a shorter path? Yep. And what is it? ABCZ, ABDZ, there we go. ABDZ, which is 9 plus 7, right? 9 plus the rest of the way, which is 7, gives us 16. And, you know, we do another thing down here where, you know, blah, 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 but I'm out of time. So we found it, it's 16, ta-da, it's great. I am out of time. So I had a bunch more I was gonna do, so that's not great. I was gonna do another example and talk to you about the lab, but I can't do either of those things. So I'm going to just turn you guys loose on the lab this week. I think you'll be able to mess around with it and see what it's trying to do. Essentially what it's doing is it's drawing a tree in 3D space using cylinders. And what you can do is you can modify different parameters of the program to draw the shape of the tree in different ways. You can change how many branches there are, the arrangements of the branches. A lot of the things are randomly chosen, like you know, how long the branches are, how many branches there are, if you put in more branches or leave some out. And so I'll leave you to look through the code and figure that out. I think you guys will be able to figure it out. Does anyone have any further questions about this, which is more important, before we go? Yeah, we will still have lab this week. Yeah. Yeah, you should still submit it. I think you guys will be able to figure it out. Yeah, there's never enough time in this class, so my apologies. I thought we would have some time at the end, but no such luck. So no other questions on this? That all makes sense? On step 4, the edge set doesn't have DE because D is not in the vertex set. Yes, you're totally right. Thank you. Yep, that's a mistake. That should not have been in there. I agree. Yep, nice catch, Nathan. Cool. And this whole thing is in your book too. So the whole thing is described in the book. So if you want to, if this was tough to follow, which yeah, of course it was, this whole exercise is listed in your book with the explanation of how you do every little step. So you can read through that whole thing if you didn't totally follow what was going on here. And I think that would be a good review. And of course, there's more examples in the exercises if you want to try your hand at those. I believe there are some examples that have answers in the back. Yeah, so there's another one here. I don't know if anyone noticed this, but these questions that are blue instead of black, these questions have answers in the back of the book. So here's another example of Dijkstra's algorithm that has a whole nother explanation of how to do it in the back of the book if you want, you know, another good example for how to do that guy. Okay, any other questions before we go? Okay, well, have a great weekend, everybody, and I'll see you next week. Bye, guys.